Hello, welcome back to Graph Theory. In this video lecture, we're going to take a look at some material from section 9.3 in your text about duality in planar graphs. We already kind of met the notion of duality when we were converting our map coloring problem into a vertex coloring problem. So in this lecture, we're just going to kind of formalize some of those ideas. You can see the outline there. I want to define for you what I mean by the dual of a planar graph. It's denoted by G star. I want to look at lots of examples just to get you kind of used to some of the nature of what goes on when you're thinking about duality. And we'll prove some elementary properties of duality in graphs, but the proofs in this video lecture will actually be quite light. This is just sort of more of a survey of the topic of duality. Okay, so let's start off by making the definition here. Let me try to scroll so you can see it. To take a planar graph, and when I say that, I always mean and draw it planar, because you can draw a planar graph with crossings in it. But so I'm going to kind of be using the graph and a drawing of it interchangeably. So when I say take a planar graph, I mean a planar graph that you've drawn planar, and we'll use the usual notation. It's got order n, size q, and f faces. Okay, and then I want to define the dual graph the following way. So the dual graph's vertex set will consist of things that I'll call Fi star. Everywhere I'm talking about dual, I'll always put a star on it. And what is Fi star? Well, it's just a thing. It's an element of this set, and there's one of them for every face in G. Okay, so if you enumerate the faces in G, F1 to F whatever, however many faces there are, F sub F, I guess, then Fi star is a dual vertex. So each face in G corresponds to a vertex in the dual. And then what's the edge relation? So you'll put an edge E star in the dual graph G star if and only if the faces that correspond to the vertices, so an edge, I guess I should write here, being consistent in my notation, E star is Fi star, Fj star, so it's an edge, it's a pair of vertices in the dual graph, and that edge is in the edge set if and only if Fi and Fj are adjacent to the edge E in the graph G. All right, so there's a one-to-one correspondence between edges in the graph G and edges in the graph G star in the dual graph. So if we draw a dual vertex Fi star inside, in the Jordan curve theorem sense, of each face Fi, then we can always draw E star so that it crosses only the edge E. Yeah, we connect the sort of point that we draw in the face Fi with the point that we could draw in the face Fj, and we draw a line crossing at the edge E, the edge that's incident with both of those faces. So the graph G star is also planar. All right, because we can connect those things that only cross the edge E, and edges in this planar graph G don't cross other than at vertices. So our dual edges are not going to cross other than at dual vertices. So G star is a planar graph as well. By definition, the order of G star is the number of faces in G, it's F. The size is the exact same. The size of G star is the size of G. And because of that, Euler's formula says that G star has n faces. Right? Because Euler's formula, if I write it in down here, you remember it says that n minus q plus f is equal to 2. And in this formula, what I'm saying is that the order of G star is f and its size is q. So this number necessarily is the number of faces in G star because it's a planar graph. Okay, so you can kind of think about the dual. It has the same size, and the order and the number of faces have interchanged. Okay, let's look at some examples. Here I've drawn a bunch of graphs, G, and I drew them all in the color black. I won't bother naming them, but I'm going to draw their duals while you're watching this, and I'll draw the duals in red. So I'll just sort of superimpose them. So say starting with this 3 cycle in the upper left-hand corner of your screen there, that 3 cycle has 2 faces. So the dual graph is going to get 2 vertices. There's one vertex in the dual graph for every face in your planar graph G, right? And then the recipe is every time those faces are incident with each other along an edge, you have to draw a dual edge. So I can see that the outer face here and the inner face are adjacent along, say, this edge of that 3 cycle. So that means I have to put in a dual edge across that. The outer edge, or sorry, the outer face, pardon me, and the inner face are also adjacent along that edge. So I also have to put in a dual edge there. And finally, the outer face and the inner face are also adjacent along the third edge of our three cycle. So there, we've completed the definition. So there's your dual graph. And notice that even though G was a graph, a simple graph in some languages, what we just call a graph, the dual ended up being a multigraph. And that's true in general, that the dual will have multiple edges. I'll say more about that down below in a proposition, so I won't say it now, make the video too long, but you can see here, the dual graph is this red thing, and those two vertices have more than one edge between them. That's a multigraph. All right. What about this path of length 1 here in the middle? Let's move on to it. It has exactly one face. Yeah, it has one face. So the dual has one vertex. And that one face is adjacent to itself along the one and only edge in the graph. So the dual graph actually ends up being a multigraph of order 1, and it only has a loop. It has one edge and one vertex. So duals of simple planar graphs can even have loops in them. What about this graph over here, K1? What's its dual? That's K1. It has one face. There's the dual vertex. It has no edges whatsoever, so the dual doesn't have any edges. What about this loop down here? This loop down here, it's a multigraph. It has two faces, and those two faces are adjacent along the one and only one edge. So when we took the dual of the loop, we got the path of length 1 back. Okay. Here, let's start off with our little hamburger-looking graph here in the middle. Sorry, my description isn't that great. Here's what I mean by the hamburger-looking graph. It has three faces. So put a dual vertex in for each one of them. And then I connect those dual vertices across every edge in the graph. Yeah, so I would have to connect those things. These vertices meet across that edge. These vertices meet across that edge. So it turns out that the dual of the 3 cycle was the hamburger looking thing, and the dual of the hamburger thing was the 3 cycle. It's kind of intriguing. What about our friend K4 over here? K4 has 4 faces. Has 4 faces, 3 bounded ones and one unbounded one. So if we connect up using the dual, we have to connect each one of those interior dual vertices to the exterior. So it's not the prettiest drawing of it in the world, but if you take a second there, you can see that K4 looks like it's its own dual. The dual of K4 is also K4. Cool, so there's just a little bit of experience like writing down what I mean by the dual of a graph, and I hope you agree that, yeah, when we took that planar map and we were basically, the graph that we were coloring to talk about the map coloring was the dual of the map, viewed as a graph. Cool. So here's a couple of kind of simple observations about this stuff. I just called them propositions. These aren't necessarily listed in your text, but they're just some observations we can make. The first one, I'll just kind of narrate it for you. When I'm saying a simple planar graph, I just mean no loops or no multi-edges. Okay, so I'm just emphasizing that if you take a simple planar graph, then its dual will have multiple edges if and only if there are faces, Fi and Fj, in your graph that have at least 2 edges in common. And that's just kind of an obvious observation, because what would a multi-edge in G star be? Well, it must be a pair of vertices that are connected by more than one edge, and those vertices would get connected by more than one edge if and only if the faces that you're talking about, that are dual to those vertices, were incident with more than one edge. Yeah, so a common edge, each common edge between 2 vertices is an edge in G star. Proposition 2 is really just kind of a rephrasing of it, that a simple planar graph has a loop if and only if G has a bridge. Remember, a bridge is an edge that you take out of the graph and it disconnects the graph. And maybe more importantly, an edge in a graph is a bridge if and only if it lies on no cycle. Yeah. So here, that's kind of the spirit of the proof I'm going to give, is that G star has a loop if and only if G has an edge that doesn't lie on any cycle. Because you can see in the proof here, if a bridge, so since a bridge can't lie on any cycle, then the faces, the plural is kind of a fake there, on either side of the bridge are actually the same face. Yeah, because if this edge is on no cycle, then it doesn't have a kind of inside face and an outside face around it. They must be the same face. And that face is a vertex in G star, and then the edge that corresponds to that bridge must have that vertex on both of its endpoints. It must be a loop. And conversely, any loop in G star must have correspond to an edge that had the same face on either side of it. By the Jordan curve theorem, such an edge can't lie on a cycle. Yeah, if that edge was on a cycle, then the two faces on either side of the edge would be distinct by the Jordan curve theorem. All right, so you can kind of get a sense for if I don't know if this isn't scrolling that well, but if you look back in our examples, anytime that we had a graph with a bridge in it, say for example this one, then it has a loop. Got a loop. And in fact, that's the only graph that I drew that had a bridge in it. All right. So you can play around, maybe stop this video and draw a couple of planar graphs, draw one with a bridge, draw one without a bridge, and so on, and kind of play around with these propositions. Cool. We gave this definition before when we were talking about planar graphs, the length of a face. I talked about it in terms of the total lengths of all the closed walks bounding the face. Here's an alternate definition that's equivalent to it. The length of a face in a planar graph is just the degree of the dual vertex that corresponds to that face. So notationally, the length of the face Fi is just the degree of the dual vertex Fi star. It's an equivalent definition. So if we remember some things we know about vertex degree sums, then we can get this proposition. We actually have already used this kind of idea, but in a planar graph G, if it has size Q, if you sum the lengths of all the faces, you'll always get twice the number of edges. Well, and the proof of that is that a graph and its dual have the same size, and we proved that the sum of the vertex degrees in any graph is always twice the number of edges. But the sum of the vertex degrees in the dual graph is just the sum of the lengths in G. So that's just really a kind of remanifestation of that very first result that we talked about, that the degrees of degrees in a graph always sum to twice the number of edges. Here's a theorem that I took from your book, Theorem 9.10. It comes from section 9.3, I believe. And the author, maybe one of you guys can correct me about this in the Zoom class if you want, but I stated this verbatim from the book. So the author says for a planar graph G, the dual of the dual is isomorphic to G. Okay, so let's look at an example here. Oops, wrong pen color. In this example, my graph G is this disconnected graph. G is equal to, how would we write it? It's just P1 union P1, two paths of length 1. That graph has exactly one face, so I made one dual vertex, and then that dual vertex has to get connected with these two loops because you have to connect it across each of the edges in the graph G, all right? So there's your graph G, and I've drawn G star in red. Okay, so then I took a copy of G star over here, and I'm drawing G star star in blue. So what did I do? I took a vertex for each of the 3 faces that G star has, 2 bounded faces, 1 outer, 1 unbounded face. And then using the recipe, I connect vertices across edges. So according to your author's theorem, the graph G, which is disconnected, P1 union P1, is isomorphic to this graph, which is connected. It's a path of length 2. So your author's theorem is false. There's no such theorem for a planar graph G. The dual need not be the dual of the dual need not be isomorphic to G. We have an example in front of us. The dual of P1 union P1 is P2. And P2 is connected. P1 union P1 is disconnected. Those two graphs are not isomorphic. They're absolutely not isomorphic. So maybe I just wasn't reading your book carefully enough. Maybe your author threw in something in the fine print somewhere, but here's the theorem that I think that they intended. For a planar graph G, the dual of the dual is isomorphic to G if and only if G is connected. So that's how I was able to create that counterexample above, is I started with a disconnected graph G. And if you start with a disconnected graph G, then the dual will never be isomorphic to it. Again, stop the video and play around with it a little bit. Draw some small disconnected graph, draw its dual, draw that dual. You won't get the graph back. But if you start with a connected planar graph, you always will. All right, I'm not going to prove this theorem here. It's kind of a reasonable exercise, actually, if you want to think about it. Although our treatment of duality and drawing here is a little bit non-rigorous, but you could definitely reason out to yourself why, if the graph is connected, why the dual of the dual will be isomorphic to G. Okay. So one more little result here I wanted to share with you that kind of relates back to an older topic of ours, that is Eulerian graphs, that if you take a planar graph G, its dual will be Eulerian if and only if the length of every face in G is even. And really, this is a theorem. I'm taking it from West's book. And this theorem 616, if you look in that reference, it actually has some more content in it. I just kind of selected this. But I wanted to bring it up because we've said that the degree of a vertex in the dual graph is the length of a face in G. Yeah. So if all those face lengths are even, well, then the degree of the vertices in G star would all be even. And here I'm throwing you another little exercise that no matter what G is a planar graph, its dual is always connected. So by theorem 5.1, if you have a connected graph, all of whose vertices are even degree, it's Eulerian. Yeah. So if G is planar, then and its face lengths are all even, G star will be an Eulerian graph. And conversely, if G star is Eulerian, it's connected and has all even degrees, then every face length in G would have even length. Cool. All right. So in the last example I want to do in this, what I hope is a reasonably short video, is I want to take two drawings of a graph here. So you can stop the video here for a second, but I've drawn two graphs here, but they're isomorphic. I've got a graph, say G1, and a graph, say G2, and G1 is isomorphic to G2. Stop the video and kind of convince yourself that those things are exactly the same graph, just drawn differently. So they're two planar graphs with two different planar drawings, or fancy language, two different embeddings. And then I'm not going to make this video long by dragging you through the whole construction of the dual down here, but stop it, stop the video. I know my drawings aren't all that pretty, but what I did is I can at least kind of highlight in here, I drew a vertex for each of the, can you see that the graph G1 has 1, 2, 3 faces? So there's this face, that one, and then the unbounded face. And then I had to connect those things across edges when the faces bounded each other. So for example, this edge is there because those two faces are bounded across one of those 3 cycles edges. This edge because of the other edge on the 3 cycle, and so on. So stop the video and check it out. You can see that I've drawn the dual graphs correctly. Now, this isn't at all obvious, I don't think, but those two dual graphs, G1 star and G2 star, they're not isomorphic. They're not isomorphic. I'm going to let you stop the video and check this out. But if you look at their degree sequences, the graph G1, it has a vertex of degree 3. It has a vertex of degree 6. I think it's this one down here. Is it 1, 2, 3, 4, 5, 6, 7? No, sorry, that vertex has degree 7. This vertex inside the box there has degree 6. 1, 2, 3, 4, 5, 6 edges. So its degree sequence is 3, 6, 7. All right. G2 star has the same order, It also has 3 vertices, but its degree sequence, I'm not going to verify it. You can stop the video, is 349. So 2 graphs that don't have the same degree sequence are not isomorphic. So this is kind of a surprising result to me anyway, that the dual of a planar graph depends more than just the isomorphism class of the graph. It actually depends on the drawing. It depends on the embedding as well. If you embed a graph, a planar graph in the plane in 2 different ways, then the dual graph can actually, and the two corresponding dual graphs can end up being non-isomorphic to each other. So that's kind of a surprise. Okay, so that's just a little bit about what I wanted to tell you about duality. Not so many results about it, but a few of them, and it gives you some sort of a glimpse into what people might kind of do with this stuff when we talked about our colorings. All right, so thanks for listening.